Good morning. So today we're gonna go through the basic idea of classical modeling when it comes to system modeling, or some people call it design and simulation of mechatronic system. So the idea of system modeling is to basically convert mechanical systems or electrical systems into a certain simulation that we can work around with. So in this subject itself, we usually work with control systems, and in control system we have something such called as a transfer function, and using transfer function we're able to simulate it. So I will just go through. We'll get right into it. So the first thing you need to understand is that there is always something called flow, and there's something called effort. So what is flow? Flow is basically a physical quantity, a physical flowing quantity, or a flowing variable, a physical flowing variable. And then we have effort, which is basically the product of that flow. So when it comes to something like, if I were to say that we have a pipe, so I would draw a pipe like this, maybe like that. I think this is okay. So usually what happens is that we have water that's flowing, or in this case, in terms of water, we say current. And the product of that flow is actually pressure. But instead of pressure, we say it's voltage. And in the German way of writing voltage, we use U instead of V. The reason is because they don't want to confuse it with velocity. And the velocity part is actually very important, because we also have the flow, the mass, anything that has mass that is flowing or running, a mass that with a certain velocity. So in flow and effort, in terms of electricity, we have current that is flowing, and the product of that current is voltage. And when we have a velocity that's flowing, the product of that velocity is force. If you ever if you ever wonder like why velocity and force, you need to see that when you have a mass that's moving in a certain way, it has inertia, and therefore then it has a force now. So if you have mass that is moving in this direction, we call it A. So therefore you know that MA is moving in the opposite direction, and we say F is equal to MA, meaning the force is in that direction, in this case is FM, and inertia is in the opposite direction, which is on the other side. So going back to our flow and effort, flow variable and effort variable. So when you have velocity, this is in terms of linear motion, but we also have rotational motion. So in rotational motion, it would be angular speed, and the rotational equivalent of force would be moment. And also, we in terms of water, we have the flow rate and the pressure. So you will notice quite, if you may or may not notice this, but you can actually look at this. You could say that actually P, P is equal to IV or IU. Because I came from a British school, we used to say V instead of U. P is also equal to FV, P is also equal to MW, and P is also equal to PQ. In this case, this is power, and this is pressure. So we're going to start with electricity first. So when it comes to resistors, we know a very basic electrical formula, which is Ohm's law, which we know U is equal to IR. In this case, we would arrange it as U over I is equal to R. Hence, we call this our transfer function GR. Now, if you're not sure what is GR, so basically when you learn this in control system 1 or control system in general, a control system is you have a block, and you input it, you have a certain input, and then you have output, and then you have a transfer function. We call it, for example, GS. Just accept that GS is a transfer function. So a transfer function is nothing but just the ratio of the output over the input. Because your output is usually smaller than input, but it's not always smaller than input. You could be having an amplifier, and then your output will be larger than input. Of course, this would then require maybe additional power, or some additional current somewhere, depending on what you put in. So just remember, a transfer function is just output over input, and in this we equal to GS. And your GS could be several equations over something else. So that is the mathematical part of transfer function. Many students in my degree struggle with this subject because they're actually exposed to this course before they actually enter the higher semesters, where they actually get to learn on control systems. And yeah, so as we move on, so from here, when you have this block itself, we're going to say that we have a block R, and our input, just like I was saying, our input is the effort, the input is the flow, and our output is the effort. So you input current into a resistor, and what do you get? You get a product of that input, which is the voltage itself. Yeah. So this is in terms of electrical. Now, when we talk about mechanical linear, the voltage equivalent of the mechanical linear equivalent of voltage instead of U would be V, which is velocity. And in velocity we write, because velocity is a product of dx over dt, and v equals to dx over dt, yes, and it's also equal to f over d. So if you're wondering what is d, d is basically a damper, or in English we actually call it suspension, but the Germans call it a Dampfer or damper. So in this damper, it has like this was a resistor, so we call this R, and this is equal to D. So in this damper, your professor, depending on what you get, may sometimes give you, instead of D, you get instead of D you get RML, which is your mechanical linear resistance. And from this, when we bring this together, we get V is equal to F over RML. So when I say, so F is equal to V RML, a product of V and RML. And one thing from this we also know is that P is equal to FV. So don't forget that. So in this case, what would happen is that, maybe I shouldn't write that. So you could say that your effort is force, let's put it E here, and your flow is velocity. So in this block, you always input your flow and output your velocity. Your flow and your output is your effort. So input and output. So your input here would be velocity, your output will be F. And here you will be RML. So if you were to write this as a transfer function, you can write FD, or you can even write, not FD, GD, or GRML is equal to F over V. So going on, so if we have a mechanical rotation, we call it ROT, the velocity equivalent would be angular speed, and equals to M over D. In this case, this is a rotational damper. I was not told on how to draw a rotational damper in any specific way. So in this case, we also draw the same thing as a damper, but we write maybe D rod, for example. And we also know that it's also a good thing to know that omega is also equal to D phi over dt. So basically, is your it's like the angle, the difference of the angle, the rate of change of the angle over time. And from this, we can say that M is equal to WD. And we also know that P is equal to MW. So then your transfer function will look something like, which is D. Let's call it D rod. D rod. And your input will be omega. Your output is the moment. So omega is your angular speed as a reminder. So we seem to almost have everything involved already, but not entirely. So one of the things that we are missing still is in terms of liquid. So I'm just gonna circle this separately because this is really, really important. So when you just remember, in resistance you have, in terms of electrical, mechanical linear and mechanical rotation. But beyond this, you also have in terms of fluid. So in fluid, you have flow rate is equal to P, pressure, divided by resistance of flow. So what is resistance of flow? Resistance of flow is basically if you have a pipe, we call this a pipe. It is the resistance or the contact area surrounding this area. Why did we draw a pipe like this? The reason is because your pipe doesn't necessarily always have to be like this. It could also be like a hole in the wall, for example. So yeah, maybe like, so other than that, you also need to know that so P is equal to RFQ, and power is also equal to pressure times flow rate. So this would be all of your in terms of just resistance. And inside electrical systems, you have resistance, you have capacitors, and you have inductance. So that covers your resistance part. We're going to go now to capacitors. So in terms of capacitors, I think I will use the color yellow for capacitors. So just a reminder, we have done our resistor part, and now we're going to do our capacitors, and later on we'll move on to do our inductors. So in capacitor, in electrical, it's always based off electrical. We say UE is equal to 1 over CE integration of IC dt. And it's generally, this is your main formula where you're going to derive everything from. Yeah. So if sometimes you ever feel like you're struggling to remember, you can always just go back to the formulas that you always start off in electrical itself. So therefore you can easily remember them more easily. You just need to remember your main formula, like this one and this one, and then you just have to substitute the values of this. It's not very difficult. Yeah. So so in here we know that UE is equal to 1 over CE integration of IC. So when we're gonna, in order to convert this into this is for voltage. So when it comes to current itself, if you were to rearrange this formula, and you bring the left hand side to the right hand side, you will actually get IC is equal to CE multiplied by the differentiation of UCE over dt. And if you're wondering like what is UCE, UCE is the same thing as UE, is the voltage at the capacitor, and E stands just for electrical. So yeah, and the work done, or we call it the energy stored, work done, and this is in terms of joules, whatever, not like that. It's always equals to CE multiplied by UE square over 2. So you kind of know that kinetic energy, or as we call, let's call it like we say EK, is equal to mv square over 2. So you will see that you everything for work energy stored would be something similar to something like this. Now we go to mechanical linear. To make it more clearer. So in mechanical linear, we're going to base off what we wrote earlier. So what is the equivalent of UE? For UE, the equivalent is force, because voltage is the product of current. So in mechanical linear, force is the product of velocity. So it's just like here, we had the product, the flow, and the effort. This is the flow. This is the effort, this is the flow. So it's very important to keep in mind, even sometimes myself I forget, the effort is the result of the flow. You were flowing well, and therefore what came out was your effort. And in mechanical linear, so we write this formula as, so initially we wrote as 1 over CE. So in here we write 1 over, we call it the mechanical capacitance, and then the integration of V dt. So if you're ever wondering what is mechanical capacitance, so mechanical capacitance is actually mass. So in this sense, it's actually 1 over m integration of V dt. So the reason why mass is considered capacitance or energy storage is because if you were to bring a certain mass, we call it m, to a certain height, then therefore now it has potential energy. And given that it has potential energy, therefore it's considered a form of energy storage. And that is how you need to know, how you can keep that in mind to know this. So when we rearrange this formula, we will get V is equal to m multiplied by df over dt. You can see in general it's quite similar to exactly what we wrote here. Maybe I can circle this in orange to help it look better. And the work done would be equivalent to mf squared over 2. Some of my professor in the beginning, he didn't explain this idea to me, as I recall. So initially he wrote as CML to get it more specific, the mechanical linear capacitance multiplied by f squared over 2. So now that we're done with mechanical linear, we're gonna go to mechanical rotations, and later on we will go to fluid. So in mechanical rotation, we say this was force. So the equivalent of force in mechanical rotation is moment. Moment is equal to 1 over m integration of, and the equivalent of linear velocity in terms of rotation is angular velocity. So we call it w, and we put dt here to be more mathematically correct. So we now say w is also, when we rearrange it, w is equal to m multiplied by dm over dt. And it's really important to know that m is not the same as big M. This one is mass, and this is moment. So then the work done would be equivalent to m, small m multiplied by big M squared over 2. You could also say that is km rod multiplied by big M squared over 2. But I personally prefer this because I don't want to write too much. Now when we go to fluid, we say that P, the pressure, is equal to 1 over the fluid capacitance, CF, the integration of Q dt. And always remember, this is your flow, and this is your effort. And then we have Q equals to CF multiplied by dp over dt. And then work done is equal to CF multiplied by P squared, the whole thing over 2. So now we have done our capacitance. Now beyond this, we are also going to work with inductance. So I'm going to copy this. So in inductance, I'll use the color green. our main formula in electrical when it comes to inductance is always IL equals to 1 over LE. So under this case, I'm just going to put as L, and maybe I use big I. The integration of UL dt. So you may notice that we didn't have this in here earlier, but because this is technically the inductance is like a special case, so we just have to kind of accept it. So for this is our main formula that we're going to derive all our different alternative dimensional for mechanical linear and mechanical rotation and fluid. So from using this itself, we rearrange this, we know that UL is equal to L multiplied by DIL over dt. And when we go to mechanical linear, we have V equals to 1 over L mechanical linear integration of F dt. Okay, I made a mistake. In the beginning, I said that your capacitance is mass, but actually your capacitance is actually a spring. Let's just ignore that for now. So basically in here, we will also write this as V is equal to 1 over M integration of F dt. So it's always like this. And when we rearrange this formula itself, we will get F is equal to M dV over dt. And V is not equivalent to U. This is velocity. And this is voltage. And we are working with the velocity. And when we go to mechanical rotation, we say W, or the angular speed, omega, is equal to 1 over M integration of big M dt. So this is mass, and this is the moment. So when we rearrange this, we get moment is equal to M multiplied by dW over dt. And if we were to go to fluid, we get Q is equal to 1 over, I'm going to call this fluid inductance, so I call it LF, integration of P dt. Rearranges, we get P equals to L, P equals to LF dQ over dt. So that covers our introduction towards effort and flow variables in classical modeling.